Welcome to The Explainer. Today, we're going to tackle a classic computer science puzzle. How do you bring order to complete chaos? We're diving into Heap Sort, a really elegant algorithm that can take a total mess of data and turn it into a perfectly sorted list. And it does it all using a surprisingly simple but incredibly powerful data structure. So let's set the stage. Imagine you've got millions of items to sort. Maybe it's user scores, maybe it's inventory data. But here's the catch. Your system is running on fumes. You have absolutely no extra memory to just make a new sorted copy of the list. You have to sort it right there, in place. That challenge is exactly what Heap Sort was designed to solve. Now, before we can understand the sorting algorithm itself, we need to pop the hood and look at the engine. And that engine is called the heap. This data structure is the secret sauce that gives Heap Sort all of its power and efficiency. So, what is a heap? Well, you can think of it like a special kind of family tree, a binary tree, that lives by one golden rule. We call it the heap property. And all this rule says is that the most important item, whether that's the biggest number or the smallest number, is always sitting right at the top, at the root, ready for you to grab it at a moment's notice. This single property, this one simple rule, is the key to everything. It dictates the heap's entire organization, and it's what makes it so incredibly efficient. Let's see how it works. Okay, so this heap property comes in two main flavors. First, you've got a max heap. In a max heap, every parent is bigger than its kids. This has the effect of bubbling the largest value in the entire collection right up to the very top. A min heap, as you can probably guess, does the exact opposite, putting the smallest value at the top. Now, since our goal is to sort an array from smallest to largest, we're actually going to use the max heap. I know that sounds totally backwards, right? But stick with me, you're about to see why it's the perfect tool for the job. And here it is. This is the aha moment. This is the real magic behind the whole thing. While we've been picturing heaps as these branching trees, in reality, they're stored in a plain old simple array. This clever trick gives us all the power and logic of a tree, without wasting any memory on things like pointers or nodes. Let's break this down. See, on the left, that's the tree we think about in our heads. But on the right, that's how the computer actually sees it, just a flat array. The root of the tree, it's just the element at index 0. And if you want to find any node's children or its parent, you don't follow pointers. You just do some super simple math on the array indices. No extra memory, no complex structures. This is what in place really means, and it's the key to Heap Sort's incredible memory efficiency. All right, so now we get how the heap is built. Let's put this clever structure to work. We're about to see how these properties come together to create a seriously powerful sorting algorithm. Think of Heap Sort as a two-act play. In Act 1, we take our totally jumbled up array and we whip it into shape, rearranging it into a perfect max heap. Then, in Act 2, we just systematically pull the largest item off the heap, put it where it belongs, and repeat that over and over until the whole thing is sorted. So that first step is called heapify. It's this really efficient process that shuffles the elements around, basically working from the bottom of our conceptual tree upwards, making sure every single parent is bigger than its children. Once that's done, we have a valid max heap, and we have a guarantee. The absolute biggest element in the entire array is now sitting at index 0. Okay, our heap is built. Phase 1, done. Now for the really satisfying part, the sorting loop. This is just a simple, repetitive cycle that takes advantage of the structure we just created. It's like a conveyor belt that's going to deliver the next biggest item exactly where we need it, one by one. Here's the first move, and it's so clever. We know the largest item is at the root, right? So we take it and we swap it with the very last element in our heap. Boom. Just like that, the biggest value in the entire array is now in its final, sorted position at the very end of the array. Now that that element is sorted, we can just forget about it. We mentally shrink the size of our heap by 1, locking that sorted value in place. So now our array is split into two parts. We've got the unsorted heap at the front, which is getting smaller, and a growing, sorted section at the very end. But wait, that swap just broke our heap property. The new element at the root is probably some small number that has no business being at the top. So we have to fix it. We do something called a sift down. We take that new root, compare it to its children, swap it with the larger one, and we keep doing that, letting it sink down the tree until it finds its proper place. This restores the heap property, and surprise, the new largest element has bubbled up to the top. And that's the rhythm of Heap Sort. Swap the max to the end, shrink the heap, sift the new root down, and you just repeat that cycle. With every single loop, the sorted part of the array grows from the right, and the heap part shrinks from the left until there's no heap left at all. And what you're left with is a perfectly sorted array. Okay, so this is all really cool computer science theory, but does it actually matter in the real world? Oh, you better believe it does. The heap data structure, the engine behind all this, is absolutely critical in systems that you and I use every single day. You see, heaps are the heart of what's called a priority queue, and these things are everywhere. When your computer's operating system needs to decide which high-priority task gets to run next, it's probably using a heap. When a GPS app calculates the fastest route using an algorithm like Dijkstra's, it's relying on a heap to keep track of the best paths. The raw efficiency of this simple data structure is a true cornerstone of modern computing. So is Heap Sort the undisputed king of sorting? Well, not quite. No algorithm is perfect for every situation. And to really understand where Heap Sort fits in, we need to compare it to its biggest and most famous rival, Quicksort. Let's put them head to head. On average, yeah, Quicksort is usually faster in the real world. I mean, it's right there in the name. But, and this is a huge but, Quicksort has a potential Achilles heel. In a worst-case scenario, its performance can fall off a cliff and become incredibly slow. Heap Sort, on the other hand, is the definition of reliable. Its performance is a guaranteed O n log n, no matter what data you throw at it. It's a safe bet. And when it comes to memory, they're both fantastic. So what's the bottom line here? Heap Sort's true superpower isn't that it's the fastest sprinter. It's that it's the most reliable marathon runner. With Heap Sort, you get rock-solid, predictable performance. And that is absolutely invaluable in any system where a sudden, unexpected slowdown is simply not an option. This favorable worst-case runtime is basically Heap Sort's insurance policy against disaster. It's the reason why mission-critical systems like the Linux kernel have relied on it for years. It's so reliable, in fact, that some modern versions of Quicksort will actually switch over to Heap Sort if they detect they're heading towards a worst-case scenario. And that leaves us with one final question to think about. When you're building something important, something critical, what do you value more? The chance to be the fastest most of the time, or the guarantee that you will never be disastrously slow? The answer tells you everything you need to know about when to reach for an algorithm like Heap Sort.